This conference will now be recorded.
Okay, welcome everyone. Today we have basically the second part of Mark Weiss presentation. For those who are joining us today for the first time, I will also introduce Mark again, this time very quickly. So Dr. Mark Weiss worked at the National Institute of Standard Technology, NIST, from 1979. Well, NIST was called NBS until 1988. So Mark is specialized on time transfer and synchronization techniques, statistics of clocks and timing systems, and also relativistic effects on clocks. He has now been a consultant on precision timing systems for NIST and the industry since 2014. Today's talk is about time-scale ensembles in uncertain environments. So with no further ado, we'll give the floor to Mark.
Thank you. Let's see, I need to share my screen.
Let me make you a presenter. Yeah.
Okay.
You are set.
Got it. And there's the screen I want to share. So, this is the intro slide for the talk. The basic idea is that there are these things called timescale algorithms that have been used in national labs such as NIST for decades now. And they're successful, they do very cool things. But there's new research needed because when they're used in a national lab, imagine this room full of clocks and a measurement system and computers, and they are sitting there stationary, hardwired into a measurement system, and the clocks are relatively similar. For example, at NIST in Boulder, Colorado, most of the clocks in the ensemble are hydrogen masers. There are a few cesium clocks. They're also combining with optical clocks, experimental clocks that are just amazingly stable, orders of magnitude more stable. But all of the clocks have similar noise types. So what I'm going to do is review. Okay, so that's the state of the art. What's not done is when you have very different clocks on moving platforms and in highly uncertain environments, which is where we're going with cyber physical systems. You know, data centers. I hear that a lot of folks here are focused on data centers, but still, you may want to synchronize clocks across data centers and use timescale algorithms for that, where you have limited measurements against each other. If you're doing it in autonomous vehicles, you definitely have highly uncertain environments and moving platforms driving through. You know, if you've got GPS, you use GPS. But the problem is, what happens when GPS is unreliable, or you don't want to trust GPS, or it's not even there? Let's see, there we go. Here's the outline. I'm going to start out with some introductory material, a little bit review from my last talk for those who weren't there or are unfamiliar with what I mean by stability and Allen deviation and power law noise types. Those are core concepts to all of this. And then I'm going to talk about what is a timescale algorithm or an ensemble created by a timescale algorithm. Why do we care? Oh, right, the stability is later. So the quick review of the Allen deviation is later. Okay, and then that's the first part. And then I'm going to spend some time talking about what are the problems, and I don't present solutions because I present questions. Here are the questions that need to be answered. Okay, what is a timescale? It's a we take data from several clocks. The inputs are measurements of times or frequencies with respect to a specific reference clock, and that reference clock does not need to be special. You just pick one of the clocks in the grouping and that you want to create an ensemble, a weighted average of, and measure them all against that one clock. And that's the input to the time scale. The output is the ensemble time, which is an offset from every clock in the system. And you also need the statistical performance of each member, and you can create a steered realization of the ensemble time. The advantages of doing all this are you minimize a single point of failure. If you have a bunch of clocks together as an ensemble, they're all linked. If one of them fails, you can fall over to any of the others. It does not depend on a single device. You can also detect anomalies. You know, if a clock does something weird, which clocks do. Clocks do very strange things occasionally. They have anomalies. They have time steps and frequency steps and bizarre behavior. And then the other thing is you can typically get the best out of each contributor. You can combine them. It's sort of like imagining a group of workers working together and trying to get the best out of each one. Has a different thing that they're good at, and you want to combine them so that the net result is that everybody, the combined result is better than the sum of the parts. And that's a timescale algorithm does that also. Okay, so here's what we mean by measurement. You get the time of clock 2 minus the time of clock 1. And when you do that, you've got one clock, and that clock has its own systematic offsets from an ideal performing clock and stochastic or noise or random effects from an ideal performing clock. This is the stuff I talked about last time. And you know that, so you get two clocks like that, and then you measure them against each other, and the measurement system, well, you've got to account for the delay in the timing signals between the two clocks and the measurement system. You've got to account for the measurement system itself has noise, and there are perturbations in the path for the signal. This gets much worse when you've got distributed systems that you're trying to combine. Okay, the fundamental problem of trying to create a weighted average of clocks is that you really only have, if you have n clocks, you only have n minus 1 independent measures. So if you're picking clock 1, for example, as your reference clock, and you measure them all against clock 1, you only have, I mean, clock 1 against clock 1 is 0, right? There's nothing there. So you have n minus 1 independent measurements. But to take the average value of the time of clocks, to get a number that says here is the average, the output of this is going to be the average against all the clocks. You get n numbers. So you can't solve n minus 1 equations with n unknowns. Now, there are things that are done where you do mutual synchronization using a consensus algorithm. I've learned a bit about this more recently from my colleagues at UC Santa Cruz. It's very interesting stuff, and I'm trying to wrap my mind around the difference between that and a timescale algorithm. With a timescale algorithm, you're not steering the individual clocks. You measure free-running clocks against each other, and now you can provide a steered output, but that is not part of the ensemble. So to create a timescale algorithm, you have to add an extra equation. You've only got n minus 1 measurements with n unknowns, so you have to add something in order to create a solution. And typically, if you want to optimize stability, the weights have to be proportional to the reciprocal of the variance of the clocks. That's a fundamental solution to the timescale problem. So that adds an equation. So you have a sum of weights which sum to 1. Each weight is proportional. I don't know if you can see I think you can see my arrow. So that's sigma squared is the variance of clock I. And so the weight is some constant over sigma squared I. And the constant is what you need so that all the weights sum to 1, which is really 1 over the sum of all of these terms. And now everything sums to 1.
Yeah, we can see the pointer. Thank you.
Okay, thank you. And there's another way of expressing this. This is a similar equation that the sum of the weights against the predicted time of each clock equals the sum of the weights times the scale offset of each clock. I'm not going to talk about this. It's in the literature, and I just wanted to mention that this is sometimes called the basic timescale equation, but it's similar to this previous slide. I think is a little more intuitive. This I'd have to get into the details, and I don't want to go that far. Okay, so why do we care about timescales? Again, optimizing stability. You can get a more predictable clock than any individual clock, and you can get more predictable at all possible averaging times. So nominally identical clocks may not also have the same stability at short term and long term. I'll give you examples of this. Also, you can improve resilience, as I say, minimize single points of failure. I think I've essentially said all this. You can detect errors. Okay, so what is clock stability? The way you define the stability of a clock is using the Allen deviation. That's an IEEE standard. It's been that way for some 40 or 50 years. David Allen developed this in the 60s. It was adopted in the 70s as the way of characterizing the stability of frequency standards. A clock is a frequency device, and time is what you get by counting cycles of the frequency. So it's a physical system that has a frequency and a system that with states that repeat itself, and then an electronic counter that counts up cycles of that, and that's a clock. What does it mean to optimize stability? What are the problems with different clocks? What happens with clocks entering and leaving an ensemble? And conclusions. This is what I'm going to do next. Okay, so here's the Allen deviation concept, or the Allen variance concept. And for the Allen variance concept, you typically take 3 points in a time measurement. So the curve here are measurements of the time of one clock against, let's say, against a perfect clock. You've got a clock that is so much more stable than this clock that the variations in this clock are just due to the clock, not due to the measurement system. Okay, and then the Allen deviation, this is the modified Allen variance, which is what I'm going to use mostly. But the Allen deviation originally is the change in frequency. You take the change in frequency over 2 neighboring intervals. How do you get the frequency of a clock? It's the offset in rate of a clock against the reference clock. Well, if you have the time at xi and the time at xi plus n, and you subtract those, that is the change in time. If you divide by the amount of time that has elapsed between those measurements, now you get the rate, the slope of the offset of time, which is frequency. It's actually called This is a fractional frequency because it's time divided by time. It's not hertz, it's unitless. It's in, parts per 10 to the ninth or parts per billion or some expression like that. What's done with the modified Allen variance is you, instead of taking individual points, you take the average. So it's kind of a pre-filter. You smooth the data by averaging over an interval tau. Tau is the averaging time. So you average over the interval for each of 3 successive intervals, and then you take the difference of those average times against each other to get rate, and then the difference of the next one, and it's the second difference of these averaging. X bar means average, delta squared is second difference of the average times. Square it, take the average of that square, divide by tau squared, and now it's frequency, and divide by 2 because you divide by 2 to get the Allen deviation. And that's the modified Allen variance as a concept. And the result is these power law noise types. So white noise, if you think of the spectrum, white noise means that you've got constant power over some band in the spectrum. If you're looking at color, light, white light, it means you've got constant power over all the visible colors in the visible spectrum. But if you just look at the noise of a clock, suppose you've got a clock that looks like this measured against your reference clock. What is the spectrum of that noise? You can compute the Fourier transform of that and square it and do a few mathematical things to get the right values of power, and that gives you a power spectrum. And if it's white noise and you compute the modified Allen deviation and plot it on this log-log plot, it goes down as -3/2. If it's white noise, if it's a random walk in phase, but white noise, it's the same as white noise in frequency. Now it goes as -1/2 on this log-log plot. And a little confusion because the variance is the square of the deviation. So we're looking at the square root of the variance, which is the deviation. So there's a half here, because when you take the square root, that's an exponent of 1/2. So the Allen variance slope is -3, but we plot it as -3/2. White FM, white frequency is -1/2. And between those is this stuff called flicker noise. And in a measurement system, it's typically phase noise. So you can have white noise or flicker noise, and sometimes a random walk in phase in a measurement system, which is what the left-hand stuff would predominantly be. But in a clock, you typically have frequency noise, and typically clocks start with white noise in frequency. Eventually, you hit a flicker floor, and eventually they start random walking up. And then there's also this stuff which is called linear frequency drift or aging. The aging of many clocks appears like this +1 slope on a modified Allen deviation. And so the relationship between the spectrum, this is S, the spectrum in terms of frequency data, or the spectrum in terms of phase data, they simply are the integrals of each other, and that changes the value by 2 between them. And there's a direct relationship between the modified Allen deviation and the spectrum of frequency or phase. And if you're talking about frequency, the slope of the modified Allen deviation on a log-log plot, mu prime equals -α -1, or and of course, if you're talking about the the power law for phase instead of frequency, it's beta, which is α -2. And that's just the way it is. There's a whole bunch of mathematics in there. There's also this thing called the time deviation, which really takes the modified Allen deviation and adds a +2 to the slope of the variance, which is a +1 to the slope of the deviation. So white noise in phase. So this allows you to focus on the phase noise here, where you can see it going down. You can see these places where it changes. That's critical for any kind of filtering you're doing. If you're doing a PLL, you want to lock the PLL to where it stops averaging down, for example. So that's critical to know. Either if you're doing a PLL, you want to lock in phase. If you're doing a frequency lock loop, you want to lock to where the frequency stops averaging down, right about here. So that's the lock time. And here's a fundamental paper from 1971, characterization of frequency stability. All this stuff I'm talking about has been well known in the time and frequency community. It's a small community. A bunch of nerds in national labs have been working on this. Okay, the personality of a clock. Clocks have specific personalities. It could be the time, the frequency accuracy, the frequency stability. All of these different clocks have different statistics related to these things. And the assumption is the personality of a clock changes slowly, so you can characterize a clock and use that to optimize how you do the weighted average in a time scale. Okay, there are essentially two different types of timescale algorithms. There's this one called AT1, which stands for Atomic Time 1, which was designed when it was NBS in the 70s. It's now NIST. It's still used. AT1 is still the algorithm used in NIST. I created an AT2 algorithm, and I'm not going to talk about the differences so much. There are also Kalman filter algorithms, and there has to be some special stuff done to make sure it doesn't shift all the weight to the best clock. And there's been a lot of work on that also. So the general procedure is you measure the time of the clock with respect to a local reference. You remove the deterministic portions, which are the time offset, the frequency offset, and the aging. All of those are predictable deterministic properties. And now you compute the weighted average of residuals by determining the weights adaptively using the residual variance of each clock after you remove the deterministic. And you assume that the clocks are statistically independent, so that the more clocks you have, the better the system. And now you need to know the personality of the member clocks, and you determine that using the residuals. So you have an adaptive, the weight of each clock is proportional to 1 over the variance. You determine the variance as the sigma or the deviation using its RMS time offset. It's generally iterative. You use the parameters on the next cycle based on the previous cycle and the new measurements. So here's an example of this yellow line is the measurement input. The output is going to be could be your smooth estimate of the clock using a average down estimate of the frequency. It's just an indication. So weights have to include short-term and long-term weighting functions. Estimating long-term weighting functions is much harder. You can't just use one measurement cycle to determine long-term behavior. And that defines the time and frequency of the ensemble or the scale. You may need to arbitrarily restrict the maximum weight, as I mentioned. Clocks with small frequency aging can be difficult to handle because it's hard to tell the difference between a stochastic effect and a small predictable frequency aging. And the interaction between the weighting algorithm and the clock noise usually means that you've got a random walk in the ensemble time at long term. You can improve the random walk against the random walk of the clocks themselves, but you can't get rid of it. You can only average it down. So here's an example. Okay, so this is the modified Allen deviation. These are data I generated in a computer. These are not measurements. I took the performance of typical rubidium clocks, and in short term, they average down as white frequency noise. In long term, they walk up as a random walk in frequency. And these are very similar clocks. If you had this as an ensemble of rubidium clocks and you put it into my AT2 algorithm, I actually did this with these are data that I generated, starting with 1 point measured every second. So this is the clocks themselves against a perfect clock, not as you would measure them. And this is the scale output against a perfect clock. In real life, it's very difficult to actually see all this, but you know, if you're simulating stuff, you know what truth is because you made it all up. So simulation is a very powerful way of determining whether your system is working and what you're trying to accomplish. And you can see the scale is better than all the clocks. You get, if they're similar, if all the clocks were the same, you get a square root of n improvement in stability at all averaging times. The scale seems to do better than all the clocks, except at the very long term, though it's hard to tell because the confidence on the long-term estimate is very poor. And that's a feature of the Allen deviation, is as you get to longer and longer term, you have fewer and fewer data to actually measure that. Okay, so I'm going to talk about what needs to be done in this new research. And the problems are, if you've got very different clocks, like this last one, all these clocks are about the same. So I'm going to be using simulated data for everything. And I'm going to show what happens if you've got very different clocks and want to combine them. And then what happens if you're on moving platforms. And then we want to eventually talk about ensembles of ensembles and how well can you estimate clock parameters automatically and quickly, and what are things that disrupt the ensemble. And so the results of all this are going to be questions. I don't have solutions. I'm proposing that this is research I want to do that I think needs to be done for all kinds of systems, essentially in the modern ages with new cyber physical systems on moving platforms, places where you can't get GPS. So here's a good example of an ensemble of clocks that are very different. So this blue one here is a local oscillator. That's a quartz. It's a model of a OCXO, right? Oven-controlled crystal oscillator. In short term, it's dropping down as white frequency noise or flicker noise, where it flattens, and eventually it starts coming up with a random walk. And in the long term, there's this aging term, which makes it go up as tau to the +1 here. So the best clock in short term is this quartz oscillator. It's very good in short term. In long term, it's not so good. And now if you wanted to combine a bunch of rubidiums with this local oscillator, and suppose one of the clocks is this rubidium that has a periodic error in the rubidium clock. This actually happened with a certain rubidium clock because of the way the rubidium clock works. I don't want to get into the details of that, but you know, in short term, you would normally get 1 over the square root of all the rubidiums, as we saw previously. but because the local oscillator is much better in short term, it gives it a much higher weight. You know, if you had something that was 10 times better in stability, the variance is the square of that. It means it's 100 times better in weight. The weight is going to be 100 times higher, or, you know, it's going to get 99% of the weight of the scale in any measurement cycle. That's too much, and I have not limited the maximum weight. I allow the maximum weight to go up to 100%. So the consequences is that the long-term behavior of the ensemble is getting pulled up in long-term because it's stuck on this local oscillator. So what if you had a variety of rubidium clocks, which is, you know, here we've got a whole, there's the local oscillator there. You know, there's a rubidium down here, which is pretty close to the local oscillator, very good in short term, not so good in long term. And again, the scale, you want the scale to be underneath all these. You want the ensemble stability to be better at all averaging times than all of these. That is what happens if you've got similar clocks. That's what people have seen in national labs for a long time. It's a fantastic property. It doesn't work so well when you've got different clocks. One way to solve that is to restrict the maximum weight. If you look at where this curve with the X's in it is here, and I shift to the next one, you see it drops down a little bit in long term. It also goes up a little in short term. It's a little hard to see. If we restrict the weight more, it goes even better in long term, gets a little worse in short term. So that's one solution, is to simply put an arbitrary limit on the maximum weight and say only one clock can be 25 or 26% of the scale in this case. So here's another one of those where you've got a variety of rubidiums. There's no LO, and the scale seems to do better than all the clocks, but there's this sort of strange performance here. If we limit the weight, the long-term weight, it actually improves the medium-term performance of the ensemble, and so on. Okay, so the first research question is, how do we generate an ensemble time that is more stable than all clocks, even when the statistics of the clocks are very different? What I didn't include in here was how a GPS receiver performs versus a quartz oscillator, and they're very different because a GPS receiver is white phase noise out essentially forever. I mean, eventually it flickers and you get flicker noise, but because a GPS is locked to UTC, eventually you're going to average down to UTC. If you had a clock that you could average for a month, you would eventually get UTC from GPS almost perfectly. But if you want to combine multiple GPS receivers with some quartz and some rubidium, it doesn't work very well. The quartz LO is going to be 10 to 100 times better than the receiver in short term, which means it's 100 to 10,000 times more weight. You get 99.99% of the weight going to the LO if you don't restrict the weight. Is there some better way to combine these clocks when you have such different clocks? And I want to do a bunch of research on that. Okay, let's talk about clock steering. So the clocks in the scale are free running clocks. No member realizes the ensemble average itself. You have to steer them, and you can provide the offset from, so the black, these are all the input clock signals going into a measurement system. You can tap off of one of those to a phase stepper and then steer it based on the output of the algorithm and produce a steered output. You could actually do that on all of these, and they should all essentially produce exactly the same output modulo noise in the phase stepper and the clock noise a little bit and so forth. So that's what I'm talking about when I say a steered output. You know, and I'm going to skip some of this in the interest of time. There's conflicts in how you can steer if you're trying to minimize the time error. So going back to this, the steering control, the input of each of these is essentially a frequency counted by cycles. Most folks use 1 pulse per second, but at NIST we have what's called a dual mixer measurement system, which actually takes the frequency of the clock as input. And then you have to account for the ambiguity of the cycle and get the actual time of each clock. But the steering, you start with a frequency and do a phase offset for each cycle of the frequency to produce the steered output. And so if you can steer the time offset to minimize the phase error of the clock, but if you do that, every cycle you're going to do a maximum change in the time, and you end up with a lot of frequency noise in the steered output. The other thing you can do is do very gentle steering, which means the time error is going to be large, but the frequency stability and the frequency error will be small. So those two are conflicting requirements. There's no way around that. So this is just another comment. The ensemble inputs are clock differences. The overall ensemble means that you can steer the time and frequency to an external reference to produce UTC or to produce some other reference time that you want to realize. So you have to get external data. For example, International Atomic Time does that as well, and so does NIST. Okay, so if you're trying to realize a remote reference, you want tight coupling, but that produces noise, so you want to do loose coupling when the primary scale fit, so you continue to have good holdover, essentially. Okay, so now I'm going to talk about if you've got a steered clock and you're trying to realize the steering and you're on moving platforms, and so the measurements are there's going to be a latency between when you do the measurements and when the steering is realized. So this is exaggerated a bit. To have a latency of 5 seconds, you're going to have a lot of stuff going on between the measurements and the steering, but the point here is that the scale without latency, again, this is all simulation because we know what the answers are. So the output scale in short term is worsened by the latency. So that's with 5 seconds. With 10 seconds, it gets a little worse. Okay, so now I'm going to talk about moving platforms. And of course, if you've got platforms that are moving relative to each other and you're sending signals back and forth to try to do measurements against each other, there's going to be some error in the position of each of these moving platforms, the position and velocity. And so I imagined in this case that you had aircraft and they're flying around, or drones, and they're flying around, and you're trying to maintain ensemble time in drones. Suppose you're in some situation where you can't depend on GPS, either because you're in an urban canyon or a GPS denied area, and you're measuring them against each other. Well, there's going to be errors in the range, in the position of these drones. And that's, so here I'm going to say there's I'm sorry, I said 15 minute, this is 15 second. So suppose there's a periodic effect in how the drones are trying to form around each other, and there's some error happening in their positioning at with a 15-second period. They're moving in and out, and so the actual measurements, so suppose they each had rubidium clocks. This is what the noise would look like in TDEV, and the result on the clocks themselves would look like this against a perfect clock because of the measurement noise. But the scale is actually able to filter that down a little bit. That's very cool. Is there some way we can optimize that? Of course, increasing maximum or limiting maximum weight brings down some of the long term, and that does something. But can we optimize the performance of a distributed system on moving platforms? That has not been done. If you're looking at satellites in orbit, the latency can be large, some tens or hundreds of milliseconds. Can we optimize the effect of filtering on the range errors by the ensemble? So these are things that have not been done. It would be interesting to see, is there some way to tweak some of these timescale algorithms? And then finally, if we've got uncertain measurement environments and suppose you've got autonomous vehicles, moving platforms, suppose you're in a military battlefield where GPS is denied and you need to do positioning and timing across multiple areas. You've got certain areas that you can get good measurements. So you produce an ensemble where you do have a certain reliability and trust of the measurements, but then from one island to another, is there some other kind of algorithm we want to apply to do ensembles of ensembles? So, and then clocks will enter and leave the ensembles. There are problems with that. How do you quickly estimate the clock statistics? If you're in short-term behavior, you could converge relatively quickly, but long-term behavior takes a long term to learn accurately, and a high weight clock leaving the ensemble can suddenly disrupt it. So we're going to want to minimize these disruptions to maximize our ability to use clocks that are entering and leaving. So we want to be able to increase the weight of a new clock quickly, but not too quickly because we may not trust the clock. So that leads to the last set of questions. How can we estimate the personalities of clocks in uncertain ensembles? What are optimal methods of statistically estimating clocks? What can we know about clocks if the clock that enters can say something about itself? I'm a rubidium. Here are the parameters I know that I have that could help. How can we trust that, and avoid spoofing effects? And that's the conclusion of my talks, that timescale algorithms have very important advantages. They do really cool things. I'm going to leave some time for questioning and discussion. Are there ways to optimize these algorithms for a high variety of clocks on moving platforms in uncertain environments? This has not been done. There's plenty of work that has been done, lots of information about statistics and ensembling. And thank you for your attention. I'd like to open it up for questions. I see there's some chat. I haven't really been reading it.
Yeah, you were busy presenting, sure. Mark, we did receive a bunch of questions.
Okay.
So first one, we'll let Ahmed go.
Sure. Yeah, like I think toward the end, you already elaborated on those research questions. I wanted to basically know more, like, let's say, when it came to, you were saying like combining like multiple local oscillators, like with respect to GPS. Let's say you have the GPS receiver. Yeah. Like there was something you said, like you would like to do research on that. Like, can you elaborate more on that?
Definitely. So I'm going to go all the way back to when I was talking about the modified Allen deviation, and look at this slide for a second and imagine imagine like a quartz oscillator. It has this white phase noise in short term, comes down very rapidly, is very good in short term, but then quickly hits a random walk and a drift or an aging process and walks off. So if you've got a quartz oscillator and a GPS receiver, somewhere around 10, 100, maybe even 1,000 seconds, the GPS receiver is much better in long term than the quartz is. What people typically do is they simply have one quartz oscillator and one GPS receiver, and you lock the quartz to the GPS at that crossover time. You find, what's the optimal place to lock so you average down with the quartz, you average the noise of the GPS down, and in long term, you lock to GPS. Well, that's great if you've got GPS and you trust it, and you have a system with one local oscillator and one GPS receiver. That's great. What if you have multiple clocks and you want to get the best out of all of them, and some of them are quartz, some of them are rubidium, some of them are cesium. You've got GPS receivers, you've got some noisy GPS receivers, you've got a GPS receiver that is better than everyone, but you don't want to put all your eggs on that one basket, because when that receiver dies, because everything dies at some point, when that has some failure, if that has 99% of the weight, your ensemble will just jump. You'll have a big problem. So what are the algorithms I've seen do really well when the clocks are very similar, but going all the way from a quartz to a GPS with some rubidiums or cesiums in the middle, they're very different kinds of noise configurations. I want to see if there's some algorithm that can optimize all of that sort of automatically.
Thank you. There were two comments by Warner and Jonathan about the best clock algorithm. It's not in the form of a question, so maybe Jonathan, would you like to comment?
Hi, Jonathan.
We can't hear you, Jonathan. You're double muted, I think.
Still muted.
Oh.
No, it's, yeah, no, it should. No. It's not the software, it's probably a different microphone or something.
Maybe can we go with the chat?
Maybe we can go with Warner. Warner had also something to add.
Oh, I was I did some work at Timing Solutions with Stam Stein in the 2000s, and I just wanted to share a paper. The only paper I could find on his Cas2 algorithm, which is somewhat more vague than the papers I worked from when I worked with him, and the algorithm briefly is it would use the noise spectral density of the different clocks and then the measurements of those clocks over time to figure out how much it could trust a clock at any given time. And you would set up the expected noise spectral density and go from there. And there were all kinds of add-ons for dealing with the kind of effect Marks were talking about, where you would have a clock leave. Well, what do you do? How do you make sure that the clocks that remain don't have a big step in the time scale? So I just thought I'd share that, and that might be some further background for Mark's talk. And if Mark was familiar with this algorithm and had any comments on them, I'd be interested to hear.
Yeah, Cas2 was one of the early Kalman filter algorithms that seemed to work very well. At all the publications I've seen about it, Sam seems to be trying to reserve the algorithm as a product for Timing Solutions and later Symmetricom and whatever it is, it's now microchip, but he didn't give the recipe. He didn't give it away, so you have to kind of guess what he's doing. And he's a really bright guy. He's doing really cool things. If you have public papers you can share, I'd be interested. You might have one I haven't seen.
Okay, I have this one, and there was a second one that Timing Solution shared on its website that now that they've been bought and the websites have transitioned, I no longer have a pointer to that. I'll see if I can get you a pointer to if maybe something you've seen and maybe not.
I can't see the chat anymore. I don't know how to use this for some reason.
Yeah, the chat I shared a 1992 paper that I was able to find with Google.
Was that a PTTI paper?
I think it was. It's on a military site now, but I think it was presented at PTTI in 1992.
Yeah, I'm pretty sure I've studied that paper. It's very cool stuff what he does, and there have been other Kalman algorithms since then, and a number of people have published details on how to optimize Kalmans. But I think one of the things that he did, at least his claim, was that he optimized the ability to enter and new clocks in the scale optimally estimate the parameters. But just theoretically, estimating the long-term performance of an oscillator, you really can't do that very well with a short interval of data. I mean, if you're talking about long-term performance, how can you know what it's going to do over a month of data if you've only got 10 seconds?
Horizon of prediction. Yeah, it's like it's a classic problem of like estimation from how much you have in the past.
Yeah.
Do you know work about this, Ahmad?
Yeah, I worked on chaos theory in the Lorentz model, basically for estimating things. So what I have, like if you look at the time card, and for everyone else, like timingcard.com, you see like I have all kinds of oscillators. And everyone wonders like, why do I have so many different oscillators? And that was the main reason. And then on top of that, I have environmental sensors. I have like vibration, humidity, temperature, everything. And like basically I'm trying to find markers, and I want like basically looking from the history and seeing like the correlation with these environmental changes. How are my clocks behaving with respect to one, which is the rubidium clock? So rubidium clock is a trust, and then the rubidium clock is basically gets like it's like stability from the GNSS. So and also too, yeah, a lot of things I'm running there, but there is like I'm basically the problem is like I have to build my own hardware to do my research, and that is like basically taxing my time and my energy. But like I have to do it. Like I can't buy these things. I have to build them myself. So that's
okay. But before everybody leaves, I just want to put out to anybody. Oh, there's the chat. It just showed up. I would be very interested in any information about statistical work that's been done on that would be relevant to these questions. Thank you, Warner. I just got
we have Jonathan back. Jonathan, do you want to give it a try now?
Can you hear me now?
Yes, now we can hear perfect.
Oh, fantastic. Yeah, so I guess what I had commented earlier is just take a step back. For certain applications, maybe you can sort of cut the Gordian knot, and do you actually need a single time? Because like implicitly, if you try to combine the different time sources, you're going to run into this. This is obviously a very hard problem. So I guess just like throwing out a note of like, in certain cases, is it possible to let the application choose what interpolation of sources it wants? Like if something is very latency sensitive but doesn't really care about absolute time, like a UTC or something like that, it skews towards the like the most sensitive clocks. And if it's trying to align with external systems, it interpolates and skews towards the clocks that are more accurate long term. So sort of looking at the problem from the opposite direction. And for some applications that might not make any sense at all, but for some applications that might be of some use.
So one of the things I'm hearing is I think you're talking about steered clocks, where you're trying to so that's are you talking about a synchronization algorithm where all the clocks are trying to be steered to one rate in one time?
Well, sort of both, like sort of that with everything being steered to one rate, and sort of the short-term clock being adjusted by the more accurate over the long-term clock, and steering that much finer clock along, and then just you can trust the smaller clock. Like obviously that's like an option, but more like stepping back and saying at the application level, instead of producing a single clock output value, you can choose which value depending on what the application actually needs. Like if all these clocks are available at like a system within the context of an entire system, like perhaps having the variety of clocks is actually a good thing depending on the context. So like if you have like a database that's like time synchronized, you need a master clock, like you need the most precise master clock, you need a single agreed upon value. But perhaps if you have a
whoa, I want to interrupt you there.
Yeah.
Why do you need a master clock ever? If what you want is a single agreed upon value, the timescale ensemble produces a single value that is better than any individual clock. There is no clock that is best at all averaging times.
Yes, and so my apologies, when I said master clock, I meant that like a single that refined output, if that's a good way to put it.
Sorry.
Yeah, sorry, that terminology, that's definitely was missaid. But I guess like instead of at the application level thinking of you have this refined value, but you also can just access some of these other individual values, and that data might actually be useful. It's a more general comment than like saying this is the way to provide that refined output. Does that make sense?
So for example, there's other parameters that are hard to put in an ensemble, like if you're using a quartz oscillator to multiply up to a high frequency for transmission, the phase noise of that local oscillator is very important. And boy, you don't want to mess that up.
Mm-hmm.
So yes, I agree that in some cases the variety of clocks, as you say, it depends on the application. Yeah. But you want to do what you need. You don't want to do a lot of work just because it's mathematically interesting.
But still, having the refinement and getting the most refined clock is still of great importance for any of these side applications or like a multi clock application.
But you have to include in your comment that the most refined clock may be hard to define because there's different properties that you can emphasize.
Agreed.
Right? There's trade-offs, and you got to decide what's my trade-off.
Yeah, absolutely agreed.
Great, we're on top of the hour, and I mean, if anyone, Jonathan, Warner, anyone else, like if you guys have like documents or something you like to share with the community or something, please feel free, send it to me or Elad, and we can put it in the wiki. And we look forward for your like attendance for like this bi-weekly thing. Okay, great.
And you've got my email address. If anybody has questions or comments to me, it's on the opening slide. That'll be available online.
Wonderful. And again, Mark, thank you very much for the lecture. It's always a pleasure working with you and learning things from you.
Likewise, Ahmad.
Thank you. Okay, so let's adjourn.
Thank you so much.
Bye, everyone.
Thanks, Mark.
Bye-bye.